On to rotations. Section 5.4 is on givens, transformations, or just rotations. Okay, we'll have a little geometric interpretation to the content of this section. We'll start in 2 dimensions, so things are easy to see. So we consider a transformation that leaves all but 2 entries of a vector fixed and maps one of the remaining entries to 0. This is called a givens transformation. We then apply the matrix representing this transformation to matrices in such a way as to leave all but 2 rows and columns fixed and to map a diagonal entry to a given value. Plenty of geometry on this first part. Second part, I'm kind of at a loss to put too much geometry on it, maybe a little bit of algebra about leaving most of a matrix fixed except for something with a particular row and column. But let's start in 2 dimensions. In R2, we can use a rotation to map the vector with components x1 and x2 to the vector, the image x tilde, with a second component 0. And a first component, well, that'll be determined by the fact that we've done simply a rotation. We've preserved magnitudes of vectors in this transformation, apparently. So we'll require x1 tilde, that first component, to be actually the norm of the vector. Geometrically, we need the cosine of negative theta to be x over the norm of x, the sine of negative theta to be x2 over the norm of x, in the rotation given here. So what we want to do, what we're getting at, is we're taking this vector x, labeling this as angle theta, and we want to rotate this through an angle of negative theta. We want to rotate it counterclockwise, clockwise, back to lying along the x-axis. And that's accomplished by this type of mapping here. So we replace the cosines and the sines with the appropriate parameters in terms of components of x and the norm of x. That produces this matrix, and that should take matrix x in the xy plane, rotate it around so that it lies along the x-axis. We can check that real quick. Call this matrix Q. Then we get Q times x to be, copy it down, apply it to vector x with components x1 and x2, do your row times column thing. Here we'll get an x1 squared plus x2 squared. That's the norm squared of x, but we got a norm of x that we put out front. So that'll just produce the norm of x here. Here we'll get a negative x2 times x1. Here we'll get a positive x2 times x1. We get a 0 for the second component. So indeed, this does geometrically perform this rotation. Okay, and what we do in the following, it's not going to be entirely clear that we're talking about rotations, but I want to think of it analogous to what's been done here. We could do a similar type of rotation of a plane, even if the plane is embedded in a higher dimensional space. For example, imagine a z-axis coming out of this coordinate system, out of the computer screen towards you. Then what would happen when you did this rotation to any vertical components, any z components of rotated vectors? Well, they'd be unchanged by this type of rotation. The height would remain the same. It's the x and y values that are changing. If I take an axis perpendicular to that, a z-axis, no values of those would change under this type of rotation. That's the idea. So what we've done, if we had x, y, and z, we'd do a similar type rotation. We've even seen how to do those rotations in the past. We'd see the y coordinate of x transformed to 0, the x1 component transformed to, well, what we've got here is x1 squared plus x2 squared square root of, that's the norm of this vector. If I throw in a z component, then some things get modified. And we'll see this when we look in higher dimensions here shortly. But we're taking the x1 component and, let me say, modifying it as appropriate. So second component goes to 0, first component modified as appropriate, and all the other components, if there's components there, They're not changed under a rotation within this plane. Okay, so we're going to generalize this idea above by mapping a vector x, x1 through x sub n, calling attention to two of its components, x sub p and x sub q, to a vector x tilde, where all the components are the same except the x sub q component has been mapped to 0, and the x sub p component has been mapped to something else. What's that something else? The as appropriate, as I described it above. Well, I can't talk in terms of norms of vector x here because it's got a whole bunch of components. But I can talk in terms of this x sub p tilde thing being x sub p squared plus x sub q squared square root of. If I only had two components, then I could deal with it in terms of a norm like we did previously. So what we saw upstairs was exactly this, where n equals 2, we only had two components, p equals 1, that's the component of x, the first component of x, which has been modified as appropriate. It was this quantity here, x1 squared plus x2 squared upstairs, which happened to be the norm because there we had a vector in 2 dimensions. And q equals 2. And that's the component of x that's mapped to 0. So what we had upstairs was a really, really miniature version of this concept here. So here's why you want to think of it as a rotation. Think of this mapping as a rotation of the xq, xp, xq plane, like we had the xy plane before, that leaves the perp space to that plane fixed. Perp space in the picture we had upstairs might be just a z-axis. So we get a one-dimensional space perpendicular to this plane. And well, in general, you might have an n-2 dimensional perp space to this 2-dimensional plane. And the geometry is the same as you'd have in 3 dimensions. Well, it's hard to visualize, but the geometry is the same in terms of what this type of manipulation, which we're calling a rotation, only in higher dimensions, what that represents. So a transformation that does that type of mapping vector x to vector x tilde, where the qth coordinate becomes 0, the pth coordinate becomes something. It'll be forced to be what's mentioned above by the way we do the transformations. This is called a Gibbons transformation. Okay, might have to zoom out a little bit to see the whole thing here. Gibbons transformation, given here, performs that desired manipulation. So we're going to claim that this matrix G sub PQ produces, how's it worded exactly? A matrix which produces the Gibbons transformation is, as given here. So this will, when multiplied by vector x, produce an x tilde of this form. That's the claim. In particular, we get 0 out in the qth component. Except for the p and qth components, nothing's changed, and p changes a certain way. We've already kind of predicted what would happen there. But look what this matrix is. It's an identity matrix, except in the pth row, we've got a C along the diagonal. In the qth row, we've got a C along the diagonal. In the off diagonals, correspondingly, we've got an S here and a negative S here. So this isn't quite a symmetric matrix because the S, negative S, these are in, what would this be, the PQ entry, and this would be the QP entry. They're not the same. They're close, differ by negative. But not a symmetric matrix, not exactly an identity matrix, but awfully close. So close to an identity matrix, we're going to concentrate our attention on just these 4 entries that's given here. The 2 C's, the S, and the negative S. The rest of the behavior in terms of matrix multiplication, it acts just like an identity. It is an identity matrix, the rest of it. So the claim is that matrix performs this kind of mapping where the C value, the C value up there is chosen as x sub p divided by xp squared plus xq squared. The S value is x sub q divided by xp squared plus xq squared. And G sub pp, G sub qq is given as C, as drawn in the picture. G sub pq is negative G sub qp is S, as drawn in the picture. And so this is just laying out how C and S are determined for a given vector x in terms of the p and q components of x. And x tilde is then given by C x sub p plus S x sub q. Given the C and S values, that turns out to be this quantity here, okay? If we were in 2 dimensions and x only had 2 components, this would be the norm of x, and this would be the picture we had on the first page of these notes. Okay, so that's the claim. All we got to do is take that matrix up there and apply it to vector x. Take that matrix up there, apply it to vector x, and it produces exactly what it's supposed to. Let's maybe take a look at that. If you were to lay out a column vector x over here with components x1 through x sub n, what's going to happen? Let's see. First component of the product would be first row times the column vector would be x1. Second component would be x2, blah, 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 through x sub p minus 1. This is the pth row here. In the pth row, we get row times column. We get C times x sub p plus S times x sub q. This is the pth entry in this row. This is the qth entry in this row. And similarly down here in the qth row, the pth entry is negative x, negative s, and the qq entry in the matrix is C. So this would give us a negative s x sub p plus c x sub q. When you do the product, and all the others just produce the x's. And that is exactly, there it is, exactly what we claimed. There's the x, whoa, there's the pth entry of that matrix product as predicted, and there's the qth entry as predicted. All right, we've defined S as given here. If you'll take S times x sub p, that would be x sub p times x sub q over this quantity, have a negative out front. Take C times x sub q, that would be x sub p times x sub q with this quantity in the denominator, be the same except for the negative sign, add them together and get a 0. The x sub p tilde we're getting out is given by this quantity here. We could express it purely in terms of x sub p's and x sub q's by doing some substitution there. So such a transformation exists. We're now going to apply it not to a vector, but to a matrix. Here comes a deal where we only have to consider those 4 entries. But now we're going to generalize this and use matrix G sub PQ as given above, representing a Gibbons transformation, to transform a symmetric matrix X into a symmetric matrix X tilde with the same rows and columns as X. We saw that preservation of entries in a vector. So we can use that to give preservation of entries in rows and columns, except for the pth and the qth rows and columns. We require the pp entry of x tilde to be some given value, call it A. Okay, so A could be anything of your choosing, but we'll have to have that value when we do the computations and establishing this. We want a matrix G sub PQ is given above, such that x tilde is G sub PQ transpose times X times G sub PQ. We'll only need to consider the x tilde pp, the value A, since G sub PQ and G sub PQ transpose, they'll preserve the rows and columns of X, except for possibly the P and Q rows and columns. So the question is, what do you choose for C and S, such that in that Pth row and Pth column, we get the appropriate kind of behavior? And my only real constraint is we want to get an A out in the PP position. So if you'll restrict yourselves to the appropriate components or entries in vector X, X sub PP, X sub PQ, X sub QQ down here, X sub PQ here as well, you were given that matrix X is symmetric. So I use the same thing in both of these to have less unknowns. When you do the multiplication in terms of transposing and then the X matrix, and then the G sub PQ matrix, again, only restricting our attention to that handful of little entries, we get this relationship. So here's a piece submatrix of a G sub PQ transpose and the corresponding submatrix of G sub PQ. We want this to give us out X sub PP tilde. We want that to be value A, and any other things that come out. Question is, how do you choose C and S for this to work in terms of A and entries in matrix X? I'm going to add a little condition here. This is basically a normalizing condition. We got a lot of unknowns, so we're trying to narrow down precisely what C and S could be. Now, suppose we take C squared plus S squared to equal 1. We're just trying to find a matrix that does this. This gives us a matrix that's, I don't know, sort of normalized in some sense with respect to C and S. But this is a condition we'll impose to get a relationship between C and S. Now, do the multiplication, row times column style. For this product, it will produce this 2x2 matrix. Okay, so I guess some linear combination of linear combinations for the 4 entries. And we want this to equal this little matrix here. So in particular, we want the upper left-hand entry to equal this upper left-hand entry. We want A to equal this stuff. Let's distribute. That'll give us a C squared term, a minus CS term, a negative CS term, and an S squared term. Multiply out this 1, 1 entry, and we are really dealing with just 2x2 matrices this go around. We want that 1, 1 entry, which simplifies down to this quantity here. We want that to equal A. Okay, so the plan is to find C and S in terms of A, X sub PP, X sub PQ, and X sub QQ. You're given a matrix, and then you want to find a matrix that does this type of transforming, which means you need to find C and S in terms of given information, the components of X and the value you want X sub PP mapped to the A value. Okay, so copying that down, A equals this little expression here. Okay, there's the expression. I really want to see quadratic somewhere in there. So I see a bunch of stuff squared. Let's do the following manipulations. This is where we'll use that normalizing property here in a second. Let's factor a C squared out. Factor the C squared out. This was a diagonal entry. So we're making an explicit assumption that C is not 0 at this stage. To factor the C squared out, then we get C's in the denominator. So that's my concern. So factoring out C squared, we're left with X sub PP minus 2 S over C X sub PQ plus S over C squared X sub QQ. And I'm still wanting to see a quadratic. I got a quadratic. I tell you what, let's replace S over C with parameter T. And then we do have a quadratic. There's a quadratic. Excellent. C squared. Let's see if we can't get rid of the c squared as well, or just write it in a different form. C squared, what we had t equals s over c, so 1 plus t squared equals 1 plus s squared over c squared. Get a common denominator on this last little piece here. That gives you c squared plus s squared over c squared. Remember the normalizing condition we mentioned, so we're taking that quantity to be 1. So we get 1 over c squared here, and that allows us to say, take reciprocals on the ends of this equality, that c squared is 1 over 1 plus t squared. So we can replace the c squared with 1 over 1 plus t squared. That's the problem with a computational proof, and I can follow it. What motivated them to do these manipulations, that's not always clear. And part of it is, I'm looking for a quadratic. Well, we got the quadratic part right there. There's some other stuff in the way. We could cross multiply. Let's take this 1 plus t squared, move it to the other side. The other side was just an a. That's how we got into this. So we get the quadratic part here equals to 1 plus t squared times a, the other side of the equation, by cross multiplying. Now we got t squares on both sides. Well, let's get them all on one side. We're ultimately going, you can see foreshadowed down below, we're ultimately going for solving a quadratic. So rearrange this, get the t squares all on one side, bring this at squared to the left-hand side. It'll come as a negative at squared. Then we'll have t squared times x sub qq minus a is a coefficient of the t squared. We got a constant of a on the right-hand side. Bring that to the left-hand side as a negative. And there you go. There is a legitimate quadratic set equal to 0. And we want to solve for for t. We want to solve for s and c, but for now, we'll solve for t, and from there, we'll get the other values. So what we got here is a quadratic. The coefficients are knowns, right? We were given a. A is the value we want x sub pp tilde to be. And x sub qq, x sub pq, x sub pp, those are whatever components of matrix capital X. So in the beginning, there's capital X, and then we find this type of transformation. So we're looking for S and C, eh? All right, well, let's solve this quadratic. Solving for this, here's in the verbiage of the quadratic formula, there's A, there's B, and there's C. So we get T equals negative B plus or minus the square root of B squared minus 4AC all over 2A. So plug those appropriate things in. Of course, A verbally is playing a role that this parameter A in the slides is not, but use the quadratic equation. We get T equals this. We can factor a 4 out of that square root and do some canceling of 2's to simplify it a little bit. So we're good to go in choosing values for T if we don't have square roots and negatives. So there are real solutions to this if the discriminant, the thing under the radical, is greater than or equal to 0, non-negative. So we need x pq squared to be greater than this thing that's subtracted from it. So there's a constraint we'll have to have. We'll wrap this up in a concluding theorem here in a second. So if this condition holds, then we could choose t, say, to be, take the addition in front of the square root. Take t to be this, under the hypothesis that this kind of thing holds. Okay, we had c squared is 1 over 1 plus t squared. So c is the square root of that. C is 1 over the square root of 1 plus t squared. We'll use this t value here. We had t equals s over c. And that's what happened when we introduced parameter t. So that means s would be c times t. We got a t value up here. With this choice of c and s, then we get the desired behavior. Then g sub pq with these values for c and s yields the desired transformation. Some extra conditions came up along the way. So to summarize what we've shown, if X is a symmetric matrix, we've chosen the P's and Q's. The the P less than the Q and the way we set things up. I could always interchange those things throughout. Then for given A, any real number, provided x sub pq squared is greater than or equal to this thing here. This is the condition that said we're avoiding square roots and negatives when we applied the quadratic formula. With C equal to this quantity, S equal to this quantity. Notice everything's being done in terms of the x sub pp's, x sub qq's, x sub pq's, and the a's. Because t is calculated like this, specifically exactly in terms of those. So with this choice of C and S, where this is how t has been chosen, then we have x tilde equals g sub pq transpose x g sub pq, where g sub pq is the matrix that we had in the beginning, that Gibbons transformation. And the claim is x tilde is a symmetric matrix with the same rows and columns as x, except for the pth and qth rows and columns. And we have x sub pp tilde taking on the value a as desired. You sure x tilde is symmetric? Yeah. Transpose it. You'll get, what do you get? G pq transpose times x transpose times g pq. That's this. Oh, wait a second. I said x transpose. We're good. X was given to be symmetric. So yeah, the x tilde matrix is symmetric as well. And that takes care of rotations in the sense that our book addresses it. So a little bit left to do in chapter 5. I will see you in the next section here soon, I hope. We're almost to the end. Have a nice day.